Gil, do you want to start with the deductions?
Sure. Okay. So this session is the first of what will hopefully be an ongoing series of online conferences on microscopy, which focus on novel builds and their adoption in the wider life science community. So it's a collaboration between ABRF, so that's the Association of Biomolecular Resource Facilities, and their interest in how these technologies impact core microscopy facilities, and BINA's Builders Group, which is interested in all things related to microscope development. So we have three great speakers today. We have Paul French. So Paul French's research group is based in the physics department at Imperial, and he also has a laboratory in the Francis Crick Institute. He's made many important contributions in the microscopy field, but will talk to us today probably about his work on open source approaches to instrumentation, including interactions between commercial and open source microscopy projects. We have Nico Stuurman, who is well known for his work in life science imaging, but particularly for microscope software development, including being on the team for the open source microscope automation software that we all know, Micromanager. He's currently the director for the Center of Advanced Light Microscopy at UCSF. And we have Bryan Millis, who is a research associate professor at Vanderbilt in the Vanderbilt Biophotonics Center, where he works on novel imaging technologies, as well as being very active in the microscopy education space. He's also a leader in driving open source microscopy projects as a way of disseminating new technologies. So the talks will be 20 minutes in length, and they'll be moderated by Jessica Lim, who's a co-chair of the BINA's Builders Group with me, and it'll be followed by a panel discussion led by ABRF's Aaron Mitukas. So please keep your questions for that panel discussion. And we also have Aditi online who's available to help with any technical issues. So without any further ado, I'll hand it over to Paul French.
Okay, let me get my thing screen shared. Can you see that?
Yes.
Okay, so I'd like to thank the organisers for the opportunity to present to you today. I'm going to be telling you about work that really builds on decades of building and taking apart microscopes and building something else. So we're a physics department. I like to say we're not slowed down by a biological question. We basically build something, get the data for the figures in the paper, and generally we then need to do something else, so we build something else. And I think we run across the scales, and so we've done a fair bit of work on low-cost single molecule localization microscopy, particularly Easy Storm, and more recently with Lucy Collinson at the Crick, we've worked on super resolved Clem. My colleague Chris Dunsby has done a lot of work on oblique plane microscopy. Together we've done quite a lot of work on FLIM and FRET, and the general theme in our group is taking more or less advanced microscopy modalities and trying to implement them at throughput, so high throughput FLIM FRET, high throughput Storm, high throughput OPM. We're also doing very long-term time-lapse imaging with Eric Sahai at the Crick, and we're looking at oscillations in activation of signaling pathways. So this means doing FRET readouts over multiple days in a single assay. Whenever you're doing this kind of thing, we're doing single cell resolved tracking, and increasingly we're using quantitative phase to do that using a technique we call polarization differential phase microscopy. This is just a snapshot of 3D high content, 3D time-lapse imaging, high content analysis with oblique plane microscopy. We've also implemented multi-beam, multi-photon. We've done FLIM FRET in vivo using endomicroscopy, and we've done quite a lot of work with optical projection tomography, and we've done some work on intravital imaging, including clinical FLIM. So this has not been done by me. This is done by Chris Dunsby, James McGinty, Mark Neal, and myself, leading a group. And I would particularly like to acknowledge our kind of long-term postdocs, Yuri Alexandrov, Edwin Garcia, Sunil Kumar, and Jonathan Knightley and Hugh Sparks, who have basically contributed a lot to the work that I'll be talking about today. And so we build these instruments, and typically we're trying to build something that hasn't been done before. And at the Crick, we're trying to build the instruments that they can't purchase. And while this has been reasonably successful, we don't see that many other people using it. And so a few years ago, we realized that if we want other people to use what we do, we have to make it accessible. And so this kind of initiated our approach, which I call open scopes, which is where we're trying to make cost-effective and locally sustainable open source microscopy, enabling people, particularly in lower resource settings, LMIC context, to implement advanced microscopy. And so we've made open source versions of our instruments. This started with the FLIM HCA and multi-well plate Easy Storm. We've applied Storm, for example, to renal pathology, imaging structures that normally in the UK would be imaged with clinical electron microscopy. And having made advances in terms of cheaper cameras, cheaper imaging modalities, and so on, we decided to tackle the microscope frame, and working with Cairn Research Limited and now Custom Scopes, we came up with the open frame microscope, on which we've implemented our quantitative phase technology. And we also came up with what we call Optimal, which is our kind of low cost accessible optical projection tomography setup. And so we're building this wide range of instruments, and our goal is that they should be built from generic components, and that wherever you are in a well-resourced lab or a less well-resourced lab, you should be able, if you can build them yourselves, you can maintain them yourselves, and when something breaks, you only need to replace the thing that breaks, and you can do it yourself. And we've tried, if you want to know more about that, we have a website called openscopes.com. So what I want to go through today is open frame microscopes, which is the key part of open scopes. So what is this? Why are we doing it? How do we do it? For who is it? And maybe what are the problems that limit how we can disseminate it? And so basically, this is a schematic of a basic open frame microscope. It's built in a layered structure. Here we have the focusing layer, which here is implemented with a manual XYZ stage, a turret. We have an excitation layer with the dichroic, where we would bring in lasers or LEDs, and we have a camera switching layer where, for example, in our first implementation, which we're disseminating in Africa, we have a color camera for bright field imaging and a fluorescence camera. And this can now be put together for something like £15,000 total cost. So that's not nothing, but it's less than what we used to pay for one camera. And this is the layered structure being put together. This is Sunil Kumar, who doesn't really build it in 30 seconds, but he's pretty quick. Cairn had a competition at a conference recently, and the fastest person to assemble the microscope did it in under 5 minutes on the stand and won a prize. And so this is something that we can train biologists to do in a relatively short time. And our colleagues in the University of Cape Town now have built a version they call Traveloscope. And the idea is this is going to be sent round labs in African countries, and they've got it packaged up so we can fit it in a couple of flight cases and we can disseminate it like that. And so this is part of our program called Open Scopes Africa. And so where does it fit in with other microscopy systems? So the way I saw it is the main, in your imaging cores, you have these multifunction microscopes which can do lots of different things for lots of different users, and biologists go in, and there's usually pretty much 4 manufacturers dominating it, and so people are pretty familiar with it. You also have more advanced systems, more specialized systems. So at the top end, you might have Minstead or Lattice Light Sheet. So these are very expensive instruments, heavily optimized to do one thing really well. And you also have specialized point of care microscopes that might be for detecting kind of amoeba in water, or looking at malaria parasites and seeing where they've been optimized for a particular function. And then at the other end, you have what we have done for years, which is build it yourself. You can go to the Thor Labs catalog or Edmund Optics or your favorite vendor and put together a system. But that's pretty daunting for someone coming into it for the first time, and actually pretty expensive if you want to build a complete microscope. So OpenFrame fits in here. OpenFrame basically accelerates the learning curve. If you want to build a microscope, you have a much smaller range of components, and they all fit together in a way that gives you a well-defined optical axis. The components aligned in a straight line, and it's pretty quick to build a microscope. You can't build many other initially you can't build many other things from it, but it's fast to build a microscope and fast to understand how it works. And we use Micromanager to control this. Obviously, you could use any software you choose, but we're massive fans of Micromanager, and a big thanks to Nico, who it's going to present soon. So that was our first generation. This is the next generation. And a number of features here. We have what we call OpenTX. So this is a transmitted light module where we have a 4-color white, red, green, blue LED. We have controlled by an Arduino, and then we can do color or white bright field imaging. We can fit in our polarization quadrant optic to do polarization differential phase microscopy, quantitative phase imaging. We can put in polarizers to do polarization resolved imaging. We now would supply a manual XY stage, and the motorized stage is a thing from Cairn Research Limited called ZACT. Obviously, you can also use piezo drivers or whatever other Z stage you would like. This typically costs about 3K, and then the manual stage costs just under 1K. And so this gives you something that looks much more like a conventional biologist-friendly microscope. Custom Scopes have recently come up with a low-cost filter wheel, which costs about 1,000, and then you have to add the filters, tube lens layer, and our camera switching layer. This is a cell cam kicker. So this is a TE-cooled CMOS camera that costs less than £4,000, and it has 80% quantum efficiency and is really good for fluorescence imaging, single molecule imaging. And this is the PolCam. The cheapest polarization resolving camera now costs less than £1,000 at 30 frames per second. And so this is going to be the new generation of traveler scope that we're going to be sending to labs in Africa and so on. And then the next stage, and this is a photograph of that system with the manual stage and so on, electronically controlled Z. And then this is its big brother, if you like. This is the system that we're really excited about, particularly for implementing in Biosafety Lab 3 facilities, which we're doing now at Imperial in Cape Town. This is a very attractive thing for BSL3 because A, it doesn't cost that much to start with, and B, if anything breaks, you just switch out the component that's broken and put the new one in. You don't have to get service engineers and shut your facility while you're maintaining it. This one has motorized XYZ stage, motorized XY stage, the same motorized Z stage. We have an autofocus unit we published a few years ago, autofocus ZF. That's now been upgraded to work with an LED, works over about 80 microns with a precision of less than 10 nanometers. We are using a high power LED source for fluorescence imaging, again, motorized filter wheel and cameras, and we're putting in this microscope the polarization camera at the bottom so we can do simultaneous quantitative phase and fluorescence for segmentation when we do time-lapse imaging. So this is the current state of the art. These are the instruments that we are building now. And so this is kind of the generic view. It's a very modular approach. You have the open frame microscope at the core, and you add components which can be generic third-party components. They can be things that we build ourselves. This is a laser engine that we build using multi-mode lasers from LaserTac. These are great lasers that give average powers of about a watt, 1 to 2 watts power from a 30-40 micron stripe, so they can be coupled into relatively small core multimode fibers. And I've already mentioned the cool CCD cameras. We also have a much more sophisticated version of this microscope. This is our multi-beam, multi-photon microscope. This was built using motorized layers, which were built by Cairn GmbH in Germany. And so it's the same thing, except all of these layers are motorized, so we can do cube switching and so on. We again have our autofocus. It has descanned and non-descanned detection. And because we're trying to do high content analysis, we want to lower photo bleaching. So we're doing multi-beam excitation. We have 6 excitation beams that we scan in parallel and de-excite. And we have quantitative phase, and this is a quantitative phase image and a multi-photon film image. We have an incubator that we built for this system, which we think is very nice because normally when you have a microscope with an incubator and you want to change something, you have to change the incubator, and that's a nightmare because it's not changeable. But this is basically sandwiched between 2 breadboards, and we can do anything we like inside. And these are some images of imaging spheroids and tissue doing multi-photon film fret. And then this is an example of a technique we call TomaStorm. And so coming in on this side, TomaStorm is where we are working with electron microscopists, where basically they take their sample and they embed it in resin, and then they cut it into 50 or 100 nanometer sections. We take each of those sections and we do what we would call easy storm or destorm on that using a low-cost microscope. And the beauty of this is you can have multiple microscopes in parallel, so that you can, if you imagine this was a millimeter of tissue and you have 100 nanometer slices, that would be a lot of imaging. It could take months to years to do, but you can decrease that time by the number of microscopes you have. And these node scopes typically cost 30K. And so for the cost of one commercial confocal, say 300-400K, you can have 10 of these and go 10 times faster. Combined with a Phenom-Pharos microscope, this lets us do super resolved CLEM, which is now published in bioRxiv. And this is an example of Z-stacks of the EM and the Mito GFP labeled. And the total system costs, this is now transferred to Stellenbosch University in South Africa. And I think the amazing thing is the total system cost of the SEM and the optic and one node system is 200K. So why are we doing this? Why would people want to have modular, low-cost, locally sustainable microscopes instead of commercial instruments? I mean, I think that's obvious, but it's surprisingly difficult to convince funders of this. One is that it's cost-effective. Obviously, the upfront cost is lower. Open source hardware. Essentially, you're not paying for software. You can use generic components. You can buy them from whatever supplier. And critically, you only buy the components you need for the functionality you need. And if you want to adapt the microscope, you can reuse what you have. If you want a microscope with a new capability, you don't have to buy a whole new microscope and throw away everything that you had in the old one. You can basically just buy the bit that's new. For people like us, and for people, I'm sure, like my co-speakers who are interested, who have access to advanced microscopes, but they are developing new systems, the open frame is a way of doing rapid prototyping. You can rapidly implement new ideas. However, it does require an understanding of microscopy. And this is essentially the point. Open frame based microscopes are cheaper because you have to put them together yourself. And essentially we're relying on open source software. And so just as open source software doesn't mean free software, you have to pay someone who knows enough to use it. The same is true of open hardware. But what you're effectively doing is sharing the risk. Because the vendor doesn't assume the risk, they don't have to charge you as much, and so it can be more cost effective and critically more sustainable. In Africa, most vendors won't support microscopes. It's not worth their while. If you can assemble it, you can maintain it. You just need to send off for the new parts. And again, there's minimal obsolescence. When you upgrade, you only pay for the new functionality. So does lower cost mean worse? We would argue that this is research grade performance. You can implement almost any microscopy modality, and our aspiration is to image every modality we've ever developed on the open frame and share an open source solution for doing so. You can mix and match with commercial components, and it's permissively licensed, so it's open to all. And so basically what we're offering is less for less. It's less for less, but users need to do more. There are no service contracts which make it sustainable, and no obsolete scopes going to landfill. So why is this worth doing now? I think that we're at a kind of inflection point in technology. I mean, obviously computers are lower cost with immense power compared to what they were. Mobile phones, gaming PCs give you access to powerful GPUs. FPGA technology is very exciting. We have cloud and internet-based resources, so anyone can access ImageJ, Micromanager, and other online, Napari and other online tools. There's lots of opportunity for remote support and expertise from the community. Detectors are getting much cheaper. I think these TE called CMOS cameras at 3.5K are better than the SCMOS cameras we were buying 10 years ago. The digital image capture and processing is available for all. So again, there are people in Africa that have never done digital microscopy, and they can access that for less than $1,000. Light sources, I'm really impressed with multi-mode laser diodes. For $200-300, you can get a really nicely packaged diode. If you just want to buy the can, they cost $30. LEDs are really cheap, and there are increasing offerings out there. And of course, you can continually leverage consumer electronics. It's consumer electronics, and the demand for that is making these components cheap. Similarly, a similar story in optical telecom, fibers, couplers, and things are getting cheap because of the mass market. And of course, back to open source software, this is what makes it all possible. And again, thanks for Micromanager. And so we can do super resolution, which we are interested in, particularly getting into healthcare, replacing EM in the applications where that's used. Quantitative phase seems to be really easy now. Optical projection tomography, I'm not going to talk about, but it's very low cost. It costs less than 10K to build an OPT system. We've recently published a low cost approach to multispectral imaging using an analogous approaches to phaser imaging. And currently we're working towards lower cost versions for FLIM. That I have to say is harder. And so, yep, we want this in lower middle income countries. And if we can make these things low cost, we think it would be valuable in healthcare systems, including our own, which is always out of money. How do we do this? If somebody wants to get into it, you can buy a complete system from Custom Scopes or Cairn. You get your software from Micromanager, or you can have, there's a load of Python software and other software out there. Who is it for? It's for me. I'm never going to buy another commercial frame again. I'm basing all of my own research programs on OpenFrame. I think it's interesting for other instrument developers. I think it's really interesting for users in lower resource settings because by assembling the system, it kind of compels them to learn how to maintain it. And as you will know, low middle income countries are full of systems that were either donated or part of a research program but stop working as soon as the project ends. We know that there are several SMEs already in the UK building instruments on OpenFrame, whether or not they disclose that. We think this is interesting in imaging facilities, although that is not something that has happened yet to my knowledge. I think this would be a great tool for teaching in universities. And as I said, I'm really ambitious to get this into hospitals. And so how does this work? It's not an off-the-shelf instrument. It's not just for biologists. If you think about the regular bioimaging facility, you have a well-supported core and biologists can just go there and use it. They need some training, but essentially it's minimal training. And if they've done it once, they can do it again. With the OpenFrame, they need to work in a team. Our experience already in South Africa is that the biologists are not going to get much value from it unless they've got access to physicists, engineers, computer scientists. And this is the culture that we want to encourage. This is, of course, what we have in our labs. And so, of course, top of the end, commercial supported microscopes are better. They're the best. But is the open source approach good enough to get world-class science done sustainably and at scale? And so we believe it is, and that's what we're pushing towards. Where are we doing it? Well, we know that universities and SME in the UK are already using this. I think Cairn have sold somewhere between 50 and 100 instruments. We have OpenFrame instruments in UCT, University of Cape Town, and Stellenbosch has the Super Resolve Clem instrument. Meru University in Kenya now has an instrument with quantitative phase and wide field and soon super resolution. And we have a Super Resolve OpenFrame based system in the Indian Institute of Technology in Guwahati. And so finally, my last few slides. How do we, in our project with OpenScopes Africa, we've been very interested in how do we share bioimaging research capabilities in lower resource settings. And there've been some very interesting community-driven results. Conferences, both for example, with CZI and with the Genelia conference organized by Leon. And basically, there are kind of two approaches. Currently, the common approach is top-down, where philanthropic or other funders install high-end microscopes in centers like AMI at the University of Cape Town. And this is great. They have advanced microscopes, but the problem they have is people come from other places and their samples aren't up to much because they've got no microscopes on which to optimize the samples before they come to the high-end instrument. They have a very steep learning curve. And what we're learning there is it would be much better if there were like feeder instruments that these people could go to test their samples to image on wide field, maybe on basic confocal before going to the high-end systems. And so this speaks, I think, to the bottom up, to having distributed hubs with more generic capabilities, providing wider access. And of course, funding is an issue. In these high-end instruments, they're great, but it's not a scalable solution. And when the funding ends, no more service contracts. These instruments are very difficult to support. Bottom up, open frame, if you can build it, you can maintain it. I think the sustainability is much more likely to happen, but of course it still needs some funding. And it's still a challenge we have experienced to even get some low middle income countries to fund research at the level that it needs to done. So both top-down and bottom-up approaches are needed. And we're very grateful for Chan Zuckerberg Initiative and more recently the Wellcome Trust for giving us a chance to explore this. The Open Scopes Africa project was funded by the Chan Zuckerberg Initiative, and this was a collaboration between Imperial and the University of Cape Town, Karen Jacobs, Mike Reike, and Digby Warner. We started it with an online workshop where we had 155 attendees from across Africa. We ran an in-person workshop with 22 scientists from 11 African countries, and they all came to Cape Town. And this shows that we had them acquiring multicolor, optically fluorescent Z stacks and with Micromanager displaying them in ImageJ, and then we made them take the microscope to pieces and reassemble it, and then they were acquiring images again. And they did all of that in a 40-minute session. And the very common feedback was they had no idea they could ever do that. Normally they weren't allowed to touch the microscope. And so they found that gave them a lot of confidence. We also, after the conference, we realized that most of these people didn't even have a digital microscope. And so we built a kit, which is simply an eyepiece adapter mounted to a digital camera with a USB cable to a laptop, installing Micromanager and ImageJ. So now they can do digital microscopy on any microscope. And this kit cost $150. So we sent that to all of the people who attended.
1 minute, Paul.
Okay, but there were massive challenges still, even to get these people at the workshop. Some people couldn't come because they couldn't get visas. Some people can't come because they can't get out of their very extensive teaching commitments. Some people just had very limited knowledge of microscopy. They'd never done digital microscopy before, so they have a lot to learn. When you're shipping instruments, the problems with import duty, taxes, safety, and so on are really high. You ultimately need local internal funding for this, and convincing people to do this is difficult because they don't have the confidence that they'll get a return on their investment because they don't have the experience of it. So it's sort of chicken and egg, and we're trying to address that. And I'll stop there. Thank you.
Thanks, Paul, for your talk. Nico, we will pass it on to you. And if you want to share your screen, when Paul, there you go. You might want to make it full screen.
All right.
Yep.
Well, yeah, thank you so much, Paul. This was setting up totally the spirit that I completely subscribe to. So my name is Nico Stuurman. I'm now the director of the light microscopy core at the Mission Bay campus, UCSF, and you see San Francisco here in the distance. And the beautiful bay, which kind of looks like it today. So we have sunshine and hummingbirds flying around here. To make you all jealous, I used to be a scientist in the lab of Ron Vail, and that's where this story kind of originates. And it originated in a place like this, the top of Mount Tam, where we had our yearly lab retreats to come up with ideas of what we wanted to do and what we wanted to accomplish. And so this Micromanager open source software that I will talk about originated at one of these lab retreats and kind of brought together two of my passions, and that is software development, making things work through writing code, and microscopy. And so I know I'm in a group of people here who are very intimate with microscopes. Still, just to give you some motivation of why microscopes are actually so cool, I put together some of the old work we did. So this is a screen, an image from a screen for mitotic phenotypes induced by RNAi reagents in Drosophila cells, where we had a human AI scan all these mitotic phenotypes and come up with about 200 genes that affected spindle development. That work led to finding a couple of new proteins that induced microtubule nucleation in spindles. And so you see here a biochemical reconstitution imaged with turf microscopy. And so since these fireworks are kind of like one of the cool things you can see in microscopes, I also have here a small movie of neutrophils that are attacking dead yeast spotted on glass, and another expression of fireworks here from the microscope. So just to illustrate that microscopes can show amazing things and are really worth your time. What do they look like? Here we have a bunch of these commercial instruments that Paul talked about. The most essential part of them is these objective lenses that we all still buy from commercial companies and are thankful for that. They have optical engineers who really make these low aberration, beautiful objective lenses. Microscope can also look like this, and this is an instrument that we deployed in the core, and this is one of these total custom-built microscopes, in this case a single objective light sheet, based in part on the work of Chris Dunsby, who Paul also talked about. But so the common theme is we need to control these microscopes with software. So what does that software need to do? When we untangle that, it's very clear the camera is the most important part of it, if the microscope has a camera. So we need to be able to grab images from the camera, display them, store them on disk. We need to control light sources, so LEDs, lasers, what have you, the different wavelengths, the different colors, and we need to synchronize that, of course, with exposing the camera. We need to control motors, the XY stage, the Z stage, motors in filter wheels, and all of these actions need to be synchronized. They need to happen at the right time. You don't want to take the image while the XY stage is moving or while the filter wheel is not yet in position. They need to happen in a user-defined order. The operator needs to be able to lay out the plan of what is going to happen, and that then all needs to be executed as fast and timely as possible. And to do that, we need some kind of user interface that is intuitive and understandable to the operator, and that they can be trained in a reasonable amount of time to work with to do their work. So we proposed in 2004, when our lab had multiple different software packages, to develop something. And all of these were commercial packages that we were very unhappy with. Quality back in the day was pretty low. So we proposed to create something that was open source, because we all felt very passionate about that, as a way not only of sharing, but also create a community that can feed back into the work that you're doing. So we proposed to develop this open source microscope control software. And just to give you a little bit of historic background, we wanted something that could benefit a much larger community, and I think in the end we did. We wanted to developed using ImageJ as a start. ImageJ back in the day, it was very clear, a highly successful, open, freely available software packages for image analysis that everyone had started using. So we wanted to write code to control microscopes and other hardware. And we thought, it's hard to estimate time, but we can do that in like 1 to 3 months part-time. And then below that, it also has the potential for failure or a time sink. And I think it happened to be more the time sink than the failure in the end. So I'm still working on it. So Ron Vail back in the day he thought this was a great idea, but he thought it was good to involve someone who knew what they were doing. And that ended up being Nenad Amodai. So, to summarize, what we wanted was something, a single simple interface that works with all microscopes, open source, choice in hardware. We wanted it to be good, freely available. And then what ended up being, kind of like wishful thinking maybe in some ways, but still a very good design principle. We wanted it to be cross-platform, not only on Windows, but it should also work on Mac OS and Linux. In the end, Mac OS does not have many drivers for microscope hardware, but we can still build the software on Mac OS, and some of the developers use that. And it is very feasible to run a lot of these microscopes on Linux. So apart from that, it also forces us to really not get tied in with a certain platform-specific way of writing software. So we were focused mainly on the user interface. This is a screenshot of a relatively recent version. You see there are all kinds of nice things like plate navigation. There's a nice, decent viewer. You can set up multi-dimensional acquisitions. This is something that even novice operators can be trained in an hour or so. We use it in most of our microscopes on the core, and everyone seems to enjoy using it. The long-term value in the end lies in this architecture, in my view at least, in this architecture that was set up by Nenad Amodai. So Nenad was the person who we hired to get us going, and he came up with this layered approach to creating the software, where we have what we call an core, the Micromanager core, that is an abstraction layer for devices. So when you are programming using the core, you don't have to think too much about the particulars of each individual device. So how does it work? Normally cameras have drivers, and microscopes can have drivers. You can have serial ports to talk to things like filter wheels or light sources. So there is all you need to do in these cases is to write what we call a device adapter that adapts, that translates between a microscope driver and that Micromanager core abstraction layer. And so once you have such an adapter written, it immediately works with all other software that talks to the core. And so that ended up being a very powerful approach, and a very modular approach, and that made it possible to create hundreds of these device adapters. And you see here like our website, you see like a list of kind of everything that is there. And I think that is in the end the biggest contribution that we made with this Micromanager software project, that there is now all this open source code out there that allows microscope related hardware to talk with anything with the Micromanager core. So even if you don't use it, that open source code gives you insight in how to talk to specific devices. There have literally been hundreds of people contributing to this. So also from that perspective, it has been a major collaborative platform. All the major camera companies maintain their own device adapters. And there are a couple of hardware companies that really stand out in their support for this, like including ASI and Saber, who make this, a super important part of distributing their microscope hardware. Now, just to give you a tiny bit of a feeling for how this works, if you write such an adapter, you have to choose what type of device you implement. And you see here the current list. So you can be a camera, you can be an autofocus device, you could be a pressure pump, you could be a state device. All these devices can declare properties. So they can say, oh, I have things that are not in the normal interface, but that I want to be able for the operator to set or get. Just to give you an example, a state device, so that could be something like a filter wheel. So the calling code can ask the core, oh, how many positions does that filter wheel have? It can set that filter wheel to a certain position or get that filter wheel state. And on the state device adapter side, that has to implement a couple of functions that actually make that translation happen. And so that is how all these device adapters are programmed together. So there are some funny things then that you may run into. So another example is this shutter device where you set the shutter, set it open, true or false. You get whether it's open, true or false. So you get some kind of weirdness on occasion where, you have a filter wheel that also has a position that you want to use as a shutter. So you have a closed position and you want to be able to close that shutter. And so we have these funny device adapters that kind of translate between a state device and a shutter device, like this state device shutter here. So I won't go too much into all the details of these other interfaces. I think our camera support is amazing in the sense that there is so many cameras that are working with it. Also, this API is now 20 years old and starts to show a bit of its age. So we are thinking about how to move that forward. And I'd love everyone's input on these kind of more programming questions. Just a number of words about synchronization. So synchronization can happen in software, where the software opens the shutter, starts the camera exposure, closes the shutter, and then grabs the image from the camera. All of this depends on waiting for devices, whether they are busy or not.
Nico.
Yes, you can imagine that all takes a bit of time and is not as fast. So hardware synchronization, you rely on electrical coupling between devices, BNC cables, TTL triggers. We have a software architecture where each of these devices can declare that they can be what we call sequenced, that you can upload a sequence into the device and the triggers then cycle between the different stages of that sequence. And that way we can do very fast Z-stacks, very fast laser switching, etc. And the nice thing is that is an abstract interface where the calling code can actually calculate and see if things can be sequenced and run it very, very fast. Now, what's important to me is bringing together the person writing these device adapters and the operators. We do that in part through these devices pages, but I'd also love everyone's input on how to make that collaboration, that community at that level even better. So we have some companies who do not want the code for their devices to be publicly available. Luckily, that number is shrinking. Evident, the successor of Olympus, recently told us that we can start releasing code for their newest microscope. So I think that the culture is really changing, and I think that is wonderful. Few words on the user interface. We originally developed that in ImageJ. So Micromanager, as you know it, is an ImageJ plugin. That work was largely driven by Matsushita. We've also had Python bindings for a long time. Henry Pinkert wrote a bridge into the Java Micromanager Studio layer, which he called Micromanager. And Telly Lambert lately has been putting a lot of effort into building a Python-based user interface on top of Micromanager that has none of these Java parts. I want to have a shout out here to Mark Tsushida, who is in Madison, Wisconsin in Kevin Ellis series group. He is really maintaining all these build interfaces, the GitHub repositories, making sure the installers go out and work. This is an immense responsibility, and this is also why this whole infrastructure actually works, and Mark is doing all of that behind the scenes.
2 minutes.
Just to give you another example that I'm super excited about, we have this single objective light sheet that we deploy in the core. We train it operates fully with Micromanager. We train people in it in a couple of hours. They sign up for it, use it as any other core instrument. A big thing that made that possible is this automated deskewing and rotation. Tally's PyMM core is maturing rapidly and very much worth looking at. So a big chunk of that is the n-dimensional viewer that Gabe in Kevin's group is putting a lot of effort into. And so if you ask me now, I still think there's a big need for this Java Micromanager layer. But the future is going to be on the Python side, simply because there are way more people programming Python than Java, and the future is bright there. So a shout out to everyone who contributed to Micromanager, and I'll leave it there.
Great. Thank you so much for your talk, Nico. And next we have Bryan, our last speaker. So if you want to.
Sure. Just give me 2 seconds. All right. Can you see me?
It's loading. Yep. Good to go.
Perfect. All right. Thanks, everybody, for having me. Again, beautiful talks, although I've come to expect those from Paul and Nico. These guys are truly giants that we stand on and learn from in our own group and learn from how we deploy our systems. So I'm a research associate professor within the Vanderbilt Biophotonics Center. Just a quick bit about the VBC, because I tend to dive in right to this biomid program. That's the bulk of my talk. You know, prior to my arrival, most, not all, but a good chunk of the VBC, who's directed by Anita Mahadevan Jansen, pictured on the left here, is focused at clinical photonics. So a lot of the translational applications in photonics is what Anita has focused on and been quite successful in for a number of years. One of the things circa 2017, as I'll start to tell the story here, that she increasingly wanted to get involved with was what we now refer to as open hardware. And more specifically in the microscopy and basic sciences realm. And that's kind of where I met Anita and where this story kind of started. I'll also talk about My lab mentor, who I owe a lot of credit to, Dr. John Kozub, who's retired recently. But the goal at that time was, per the chancellor's directive, through a program called TIPS, to onboard technologies of our own development or others for the research community. And so when Anita was approached by the chancellor after a talk from Eric Betzig on Lattice, he said, "Hey, do we have these styles of technology on campus?" And what I think that the institutional level that they didn't understand was that sure, on every major campus, generally speaking, there's optics development and platform building for a specific project. But to have a resource whereby that could be leveraged for the community from a custom platform standpoint was quite unique. And as I'll tell this story, thinking about it from a programmatic standpoint is kind of the key here. And I was initially off in what I thought was going to be the hard parts of this story. So I am a life scientist, like many, I would guess, in the audience. I was just that one in the lab, like probably many of you, that enjoyed tinkering and building more than I enjoyed pipetting, and I really wanted to learn to build kind of later in life. And one of the things when Anita gave me the chance to get exposure to the physical sciences that I was really, really depressed about was that I would read about and see the data from these amazing systems coming out of these, largely physical sciences labs. And I saw the potential immediately, but was immediately frustrated because I didn't see, like in the engineering disciplines, a lot of this would end at that proof of concept or proof of principle. And you wouldn't see this come out in the commercial realm for quite some time. And I'm quick to point out that, well, I think we all know that maturation process is normal and natural for any kind of product. I think it's an important thing that people realize that the lion's share of the proof of principle or proof of concept technologies will never become commercialized. And what really suffers here is the impact that technology could have on discovery. And the reasons for their commercialization or non-commercialization isn't always linked to discovery. And so that was one of the things that really frustrated me as this life scientist / wannabe physicist or engineer, right? Which I am not, but I'm still trying to be in some sense. So in 2017, we launched this program called BIOMID, Biomedical Microscopy, Innovation, Immersion Innovation, and Discovery in a small, this is kind of when it was cleaned up, dusty old SEM room with a reasonable amount of money to bring on board open build. So the first two that we were tasked with were a single objective light sheet that both speakers today have talked about, which is largely on Chris Dunsby and Tony Wilson's work previously, and then Andy York and Reto and others have kind of iterated on this technology. And so we learned from some of these others. We immediately went to Genelia and learned, this is kind of interesting that a tidbit that I'll put out there. Whenever you go to a builder's lab and you say, hey, if I'm looking to onboard your technology, would you build it the same way you did in the paper? And inevitably, the answer is absolutely not. Right? We learned a lot during the process of developing that instrument, and we can kind of refine our guidance by the time that paper was written. And so a big part of our job initially, outside of our own development, which I'm not talking about mostly today, it's onboarding the external stuff. But a lot of what we do is the fundamental research to determine, one, what is the most impactful technologies that our institution and our collaborative partners can benefit from? And two, how can we modify it for those needs and then ease of use concerns, which we'll talk about in a minute. So anyway, we started in this room in 2017, and we built our first Lattice. And I'll talk about both successes and failures. We've built 2 Lattice light sheets at this point. We started with the Lattice, which is probably one of the most complicated builds I could have imagined from a novice builder standpoint. A lot of drinking through a fire hose in that first year. But one of the lessons I want to point out here is that we built this on time, under budget. We published in high impact papers, but we also found it incredibly hard to deploy or to disseminate. And so these are a lot of the lessons that we learned in the early days of, okay, it's one thing to build it and to successfully publish on it, but how do we get it into the hands of the most people? That's really where this rubber hits the road. Is a core environment the right place to do it? Is a dedicated facility the right place to do it? And that's kind of where I'm going with this. But we thought we were hotshots at this point. Obviously not, but we built and built and built at this point with this, newfound confidence that we could build a successful system that met spec. And we did that quite successfully, built several single objective light sheets, custom variants of wide fields that did new and funky things for very specific and custom projects, and lots of variants of orthogonal based or multi-objective light sheets. Then we kind of took that show on the road, if you will, or brought people to us. We ran workshops and taught and taught and taught. And one of the problems that we kept facing is, okay, we still can't see a model whereby this can be deployed. We can teach people what these technologies can do, but can we, for a lot of the reasons that Paul brought up in his talk, what is it going to take to get that into the end user's hands? And that's where a lot of the inertia was in our hands. And so I keep saying this, but I also want to point out that when we speak about open hardware, we can't speak about it as one style of instrument, right? We have, very deployable instruments that, a lot of thought has gone into the usability, like in the OpenScopes project that Paul spoke about. But we also have things at the complete other end of that spectrum, like the lattices of the world and, a lot of the pre-commercial variants that are very concept car-ish. My drive and my passion still is, if we remove the barrier for you using this, not maybe in the way of making it super friendly to use, but right out of the gate, if we are the ones that can help you get on the systems and we remove, a lot of those operational barriers, what new science will that unlock? And we'll talk about some of the, facilities level things that come into that. One of the huge lessons learned, which I'll talk about in a second, is this beast on the left. I started learning, tinkering and server building and this sort of thing. And I learned what it was like to try to work in the same room as a server with all of this data, which even if you do make one of these systems or build one of these systems, what is your end user going to do at the end of the day with all of that data, which is still to this day an enormous challenge for many. So one of the areas that I'm quick to point out that we kind of failed with, as did many others, we all came to kind of an agreement as a community in many ways that, many of you in the audience probably had in your grant, we still do, this trans-institutional or multidisciplinary kind of language whereby we're going to bring physicists and biologists together and we're going to do all of these beautiful things in the same room. Well, it turns out that, if you bring people in the same room that speak entirely different languages, then you can still suffer from some of the same problems. And there was this gap in the middle. And so what we were thinking originally is that we're going to take these proof of principles and we're going to package them and then deploy them in the right environment. And it turns out that was a really awkward deployment. And I won't read through all the bullet points here, but it's a frustrating experience for the end user. If you try to deploy this into a classical lab, again, we can't talk about open hardware all the same because there's plenty of open hardware systems like we've heard about that are perfectly amenable to a traditional core environment. Some of the ones that I'm talking about here that we struggled with initially, the support burden was just entirely too high for a mainstream developer or for a group that was building it to support it kind of in a core environment because you need very specialized skill sets. It's no fault of the core, but they just operate with a very different business model than otherwise would be needed to run in one of these instruments. And so I was quite honest at the time of like, wow, this was a hard fail, even though we seemingly did everything right with the build. And how do we think about this in a different way? Because my heart still bled for all of the potential discovery that these systems should be making. And so what we really came to, at least in our experience, is that there is this key step in the middle between invention and adoption that we like to call innovation, right? And this isn't a static, like, okay, we just need to modify it to do this experiment. This is an iterative and ongoing learning kind of incubator style environment. And I'll give you some specific examples of how we do it here on campus at Vanderbilt. But it starts with infrastructure like the facility that we've built here that's purpose built for kind of open hardware collaboration. Importantly, that development group, the specialists that are either building it or developing it from scratch with those proof of principle technologies, are physically juxtaposed with where they're deploying it. I can't overstate how much time is saved by having those two things juxtaposed to one another. And so this involves protocol development and external device integration as new lasers come on board or laser lines are needed or new detectors and all the things that we might want to update year over year. In a collaborative sense, we can do. And one of the key ideas here, and I don't know if Miguel's in the audience or not, but he would tell you is that, you really can direct experimentation with the complementing skill sets that are all in the same room, where we have a vested interest of a collaborator with a very impactful scientific, question that they can guide us on how to deploy rather than just building a tool and forcing it to the most possible. So after we kind of licked our wounds after our initial deployment, and we're like, okay, it was awkward. It didn't get used. It was kind of a paperweight, our first couple of systems. And we tried to learn from that experience. But our story was very powerful, and I have a number of people to thank, which I'm not even going to try to do here in this condensed environment or time frame. But there were a number of people that supported the idea and saw the promise of it. And so there was available, what we called shell space that could be built out, that we were financially supported by the institution to build out for the purpose, specifically built out with open custom hardware deployment in mind. We share the facility, or this building rather, with a number of disciplines and expertise in facilities that are very, very complementary. What we do is kind of a tinkering and building group, a nanofabrication group downstairs, for example. Electronics people that we can go consult with when it's over our head and there's a sort of too complex of a circuit that we don't want to try to design from scratch. So up at the top right, you'll kind of see my color legend here, where we start with invention, where we have an innovation space, which I'll show you some pictures of, which kind of looks like, for me, it's my dream workshop, right? It's tooling, it's spare parts, it's tinker space, it's modification space and optimization space. And then you walk directly across the hall through the image analysis suite to where all the systems are deployed, right? And these where the users are coming in and using systems and asking questions and doing image analysis and this sort of thing. Again, that was key to some of our successes. So the innovation space, as I said, I probably should have waited until now to show it, but really any and everything. So when a collaborator comes to us and says, "Hey, I have this wild and crazy idea," we first ask the question, can it be solved by a turnkey instrument? That's a really important question that we lead with. We did this just yesterday, and there are plenty, perhaps the majority of people, who I will first suggest, hey, if it can be done on a commercial instrument, that is the easiest possible path for you to go. And we will direct them to the core where they should appropriately do this experiment. But if it's something that cannot be addressed, or let's say phototoxicity is too high and they need a custom, light sheet design or any number of permutations, then this is kind of the space that we will entertain that for optimization, full-on builds with new grants and this sort of thing. However, a lot of times when people think about development, they think about a lattice light sheet or an open scope or something like this, where the developers are just designing things from scratch and then building an impressive platform around. We, right now, well, it's kind of a mix right now. We are doing a fair amount of development, but I don't want to understate the amount of tinkering that we do simply to get new and clever samples on a scope in a new creative way. So this involves a lot of design and fabrication around parts, bits and bobs, and all the tinkerers in the audience know probably what I'm talking about. There's one style of development that takes a load of your time just to develop the imaging platform. There's another to entertain wild and crazy samples. And I don't have a time to right now to go into all the different samples that we've imaged, but it's fair to say almost every new collaboration comes with a new fabrication of something crazy that we need to bolt on and image in kind of a new way. So that's a lot of the innovation that we do in that space.
5 minutes.
All right, so 5 minutes? Okay. So then we have our deployed spaces where a lot of the action happens from a collaborative standpoint. So if my boss, Anita, was here, she'd say, how, or many people will ask, we'll get into this in the Q&A, how do you float the boat financially and run, an operation like this? And what we like to say is, papers and grants are our currency. We don't do an hourly charge for these instruments. It doesn't make sense, and we can talk about the reasons for that later. But this just gives you kind of a vignette of all the different systems that we have. Each is in a separate, isolated room with wildly different samples depending on the day and depending on the system that we have deployed. We cannot talk about open hardware, especially these days. Anytime light sheet comes up, data comes up in that same conversation. One of the things that we can't do is let people leave with stacks of hard drives. It is where the data goes to die, because a lot of mainstream labs certainly don't have the capability. Well-funded labs don't have the capability to handle 100 terabytes of data when they go back. And so one of the keys to our deployment is to have remotely accessible compute. And that involves both temporary storage, we're not a long-term storage facility, as well as software access, and the raw horsepower of the compute itself. So, the GPUs and CPUs that people need to do the plug and chug with. Lots of different applications. Again, I don't have time to go into this now. The fun part of what we do is we are not the ones that ask the impactful biological questions. We never know what walks through the door, and that is the fun of my job. I would not entertain a job where I am everybody's favorite middle author unless I thoroughly enjoy doing exactly this. And we see just about everything. If there's something here that intrigued you, email me. I'm happy to talk about any of this data. But fair to say, we image a little bit of everything. So I'm not going to talk about specific use cases here because the rest of the presentation is about specific biological projects that we've addressed with some of the custom builds. But if you're interested in any of the wild and crazy imaging stuff that we do, I'm happy to talk about that in the Q&A session. All right.
Great. Thank you, Bryan. So now that we have all three speakers completed their talk, we will now open the floor to everybody in the audience. Ask any questions. You can type it in the chat, or if you want to come on and unmute and ask any questions to any of the speakers. Yes, Martin.
First of all, whoops, I think my camera, yeah, there you go. First of all, thank you all. There was a wonderful set of presentations. Bryan, you were the last one, so you kind of dodged the question though. So how do you float the boat? So I know you can't charge per hour. I've tried that and failed miserably. How do you do it?
Sure. So the first is to explain something that you said exactly right. You can't charge hour over hour. And if you're asking yourself why, I'll just quickly say that the style of instrumentation that we're talking about with some of the systems that I've mentioned here require your staff to be kind of chained to a system more than they would be with respect to like a point scanning confocal or something like this. They just require a next level of support. Which is why it doesn't, many of these systems don't end up, in a core well, other than, again, some of the systems that I've mentioned from Paul and others. So how do we float the boat? We float the boat in two ways. First, we have our own development projects where we're building systems that we write grants for in a classical kind of developmental way, tech development way. The second is all of that kind of gallery of images that I talked about. All of those are collaborations where somebody came through the door and said, hey, I have a wild and crazy idea to image soybeans or neurons or a live chick embryo or a small explosion under the microscope. If we can get preliminary data to do that, that would be wildly novel that nobody else has done before. That's the kind of experimentation that we like. So it's a bit of a loss leader model where, they will come to us with those ideas. We will get the preliminary data that they may need for the grant to the extent that we can, and we have the hardware to do so. And then we have some fantastic PIs that are successful in writing us in to those grants. And so those grants will help offset our staff and faculty costs that are in the center with respect to a percent of their effort or data storage and things, consumables and things that we need in the lab for that. And so it really comes down to that. It comes down to our collaborative activity. I'm not going to lie that it's difficult with respect to writing a grant for the specific use case of running a facility like this. It's a bit of a non-starter for a granting agency, right? Okay, you're taking technology that somebody else has built. Okay, fine, you're putting your own spin on it, and that's great, but it's not exactly novel. But then you're helping science that's not your own. It's somebody else's impactful question. So I'm not going to say it's not a struggle because I would love to have a granting mechanism that would allow me to deploy technologies like this in a much needed way, because the developers themselves do not have, and I know you know this very well, Martin, they don't have the bandwidth to support the number of users that would on board that, right? We need the life scientists coming to us to do that. And so we offset it through our both direct grants and development and then our collaborative activity. That's the long answer, sorry.
Thanks. So would you think that this is sustainable, let's say, institutional support will eventually or might eventually cease, ZCI kind of support would cease. Are you at the stage where you can support it?
Yes. Well, one of the keys here, and I say yes loosely, because I'm being terribly candid here. Yes, we can support it. We can float the boat with the caveat we run extremely lean. And what I mean by that is while I have an office that I'm sitting in technically, I'm normally in the lab, right? I'm the one writing the grants and the papers and helping get all that stuff out. But I'm also with Miguel in the lab. And then it's Miguel who has been absolutely fantastic in the lab. Miguel De Jesus, I think he might be on the call today. But he's my golden hands from a biological perspective in the lab, where he's helping collaborators get new and funky samples on some of the systems. I would love to have 3 more people. But one of our strategies right now, and I think everybody could, kind of understand with the funding environment, is that we're, shy to hire a ton of people when funding is uncertain in that way. So we run very lean.
Thank you very much, Bryan. You kudos. You succeeded where I failed.
We'll see. We'll see.
And then I personally have a question coming off of the same topic for Paul. So you mentioned that you have several of the open scopes available down in Africa. I was just wondering how much of the documentation were provided to the different lab to replicate your scopes, and if they've run into any of common issues or misunderstanding when building the scopes.
So that's a really good question. And I should say that it's a work in progress. And so our model has been to host people coming to our labs in Imperial, and we train them how to build the stuff. They can maybe come for a couple of months and then go back. And then we ship the instruments, and then we can go there for a week and troubleshoot locally. And then we are writing documentation with them. So in the OpenScope Africa project, it's the University of Cape Town that is really leading the dissemination of the platform in Africa, in the sense, and they're developing both documentation. Also, they're developing a remote support tool with like a webcam and so on, so that people can see what's happening. So it is work in progress. As we go forward, we want to produce the documentation. Primarily, we're doing that through published papers, and we want to extend that with more bespoke documentation. I think that we're not doing anything so radical that most people can't put it together from what we've published and shared on GitHub. But yeah, if we succeed in disseminating further, then we will need to probably raise our game with the documentation. The hope is that we have these hubs. So the idea is that we don't have to support everyone in Africa. Hopefully our colleagues in Cape Town can support people in South Africa, and we have a really good collaboration with a physicist in Kenya who is embedded in biomedical groups, and he's already for Nico got PIMCore Plus running a system that we sent him. And when he said he wanted to do that, we said, no, we've never done that. That's on you. But he just told us he's got that working. And so, yeah, I think it's interesting. What I would say is that if we were only going to biologists, yeah, we would need more documentation and guidance. I'm really keen on this idea that it takes a team to do interdisciplinary research, and you absolutely need the biologists, and you need but you also need people who can troubleshoot software, and you need people who can troubleshoot hardware. If people can do electronics or 3D printing, they can extend the system, make their own functionality. And another thing, I'd echo what Bryan said, is that I think 90% of the challenge is the sample, right? So like, when we're building, storm microscopes, how do you know it works? You need a really good sample. And for example, this cell line from EMBL with the labeled NUP96 labeled with nuclear pores is a fantastic tool, and so on. And so I think that the ecosystem doesn't just need hardware and software. It also needs access to reagents and test samples and so on. And there's a question in the chat. I thought there was a question in the chat for me.
Yes.
Sunil, my colleague Sunil Kumar, who's one of the pioneers of this, has answered it. It's true that Micromanager doesn't support control of some advanced microscopy imaging modes. However, we basically try to work within Micromanager, and if we have to write something in Python, then it can be called from Micromanager. The biggest limitation I think we run into is when you want to have two cameras imaging different things. For example, we have a camera running our autofocus independently of the fluorescence imaging camera. Nico is well aware of this, and we're trying to come up with a way to do that. I'm very excited by PIMCore Plus and the progress happening there, and I think it's another inflection point, right? It's really exciting to see how the software develops. I think if there's enough demand, it will happen. But coming back to the previous discussion, there is always the question of who's going to pay for it. And so if you need something for your project and you can pay for it, it can be done. And of course, if we all do that and then we share the outcomes, which I guess is the point of this community in this meeting, then somehow we can survive lean and kind of add coherently.
Yeah, I'll pile on very quickly. The reason we can run lean is because of people like Nico and Paul that make things available that we can use, right? And that, to be clear, while we're talking about open source, is not free. There are people that have to develop these tools, and that requires funding.
Yeah, and so we really need funders to understand that when they fund this, they're not even just funding one project; they're funding the wider benefit to the community.
Yeah, piling on it, funding and how we do that. So our core fully runs on recharge, including the custom built snout scope, which seems to work remarkably enough, which is a bit of a counterexample to Bryan's in the sense that it does not need that much of our attention. We literally use it as any of the other core instruments, maybe because a lot of effort went into building it extremely stable. And, to be honest, I am in part financing my activities on Micromanager through the recharge that comes into the core. Don't let that leak out to anyone. But on the other hand, that's also how we can do things more affordably in the core. And we are, have full control of a whole bunch of our microscopes, even though they're not open scopes. They're now frames, older frames that we know inside out and can repair down to the nose piece. So it's the same culture of having the technical know-how, to deal with your own equipment and kind of take over that role that a company would normally give us. And, so I think in the end, it comes down to how do we want these models to work? Do we want cores to just be a hand through to the companies, someone who's sitting in between the biologist and the companies, or do we want people who really care, about how to make, who kind of do that work that normally sales and service people do, but then are kind of much closer with the scientists themselves. And so I like that model myself a lot because, and that also includes training biologists to understand more about the technology than they maybe would want to know. Because in the end, I believe that is very important for their own experiments. And we do see a strong trend of people don't want to have to put any effort into these things anymore. They just want the data and then draw conclusions, which, okay, so I'm going around a little bit too much, but that's my contribution here.
Yes, Kevin.
Yeah, I'll just add that one thing you guys hinted at, all three of you, but didn't mention in depth is that when you think open source or open hardware, you often don't think companies, right? But companies play a really critical role in all three of your projects, particularly with Paul and Nico, and I think they could play a bigger role. There are emerging companies that could really help in dissemination of open source and particularly address issues of stability and sustaining. So could you talk a bit about kind of where you see companies' roles currently, and maybe there's several companies online here. Where could companies go to do more? So
I can say a couple of things. So obviously we worked closely. So we built the first open frame, and then we showed it to Ken and with particularly Jeremy Graham, and they saw the advantage of it. And basically, Ken's business is they don't build microscope frames themselves; they build accessories for microscopy, and they also sell systems where they would buy a commercial frame and put their stuff on it and so on. And so companies that are selling something that attaches to a microscope see the open frame as, oh, first of all, it's much cheaper. Second, it's not imported from Europe, which after Brexit is an important factor in the UK. And third, they've got complete control over it. When you want to, add an interesting scanner or some other thing to a microscope, you don't have to reverse engineer decisions that were made for a multi-user instrument that had different design constraints. And so on the one hand, it's interesting for companies that want to have complete freedom over the microscope and add their innovation to it, which is the thing they're trying to sell to the customers. But it's also interesting. I think there's an interesting business model for companies who want to sell open source. So if you sell instruments that are supported by open source software, you don't have to support the software. And software is one of the major contributors to the cost of commercial instruments, because the software development, I'm told, is often more expensive than the hardware development. And certainly the continuing support of instruments is heavily dependent on the cost of supporting software. And so companies have the opportunity to sell instruments supported by open source software where, again, they're sharing some of the risk with the user. And so the user gets a different kind of value point. And that's an interesting model, which, for example, Ken and Custom Scope are interested in.
Yeah, to add to that, I would also want to mention companies like ASI, Zaber, who kind of have their own versions of the open scope. I would say like frames that you can combine with motorized stages and etc. And they are clearly also very supportive. They put effort into making sure their hardware works in open source software, and clearly very interested in supporting that. I think John Daniels from ASI, I saw him as he may be here.
Yeah, big shout out to John.
Another company I'd like to mention is Cefla. So Cefla is another microscope hardware company out of the lab of Manu Prakash in Stanford. And they also aim to bring out commercially supported low-cost hardware that runs with fully open source software, and including the full designs of everything they built. So, yeah.
And of course, we could interact, so we can exchange. So we can use, a stage from ASI, and we can use a camera from anyone, and we can use a laser from anyone. And I think that's the power of it. Again, the community as a whole will benefit from sharing and interacting commercially as well.
The snout scope in particular that everybody has talked about today. Where would we be without the development of that objective, which is a classical case of a great partnership with industry between proof of concept and then having a solution for that lens.
Yeah,
thanks to ASI. Yeah,
exactly.
For example, OpenFrame is built ready to mount Thorlab's cage system on. Yeah, it's like, well, why wouldn't we? That's what we we typically use when we want to prototype something.
Could I just chip in about the software angle? That the shared software is amazing, and we've all used each other's things to a certain extent down the years. The issue often, I think, is that in terms of running a facility, that the open source software just doesn't have the same ease of use, slickness, attractive front end, and it's significantly more support within the facility, and it doesn't look as nice, and people get turned off from it, which is, I mean, I know, very, very shallow, but the average PhD student doesn't really care. They want the slick, fancy interface where it's easy to see what's going on and things. And the software development cost and effort is humongous for anything, and hardware is the worst because it never behaves to its spec. And then, so I don't know the best way to approach this, but I think that this is a major hurdle which, the open development has to overcome. Micromanager is amazing, but it's hard work to use.
I mean,
I want to push back against that a little bit because we're literally deploying it in our core as the main software. And, yes, we get people who are used. Inertia as a software operator is huge. I don't want to switch anything that I'm used to. So I have people here who have grown up on Micromanager and they don't want to deal with any of the Zeiss and Nikon stuff. Just give me Micromanager. And honestly, so we have very few use cases where Micromanager cannot do what the commercial software can do. I recently added a gray background to Micromanager, which made a humongous advance in like what it looks like and what it feels, so you don't have the cluttered desktop behind it. I also have to say I'm very upbeat about what Tally is doing in the PyMM core, because those are all dockable little windows that you can snap together in one big thing. So they use much newer toolkits to make the UI look nicer. So so for our core people, there's no difference in the amount of effort supporting Nikon Elements or Micromanager.
I think the inertia actually is a massive point, that we can't get people to move from a Zeiss to an Evident microscope because although the functionality is very, very similar, the software is different, and it's a lot of effort to move.
Yeah, so that is like, fair point. I understand that from people. It's like
we need a standardized interface like a car where the clutch is in the same place and the brakes in the same place and all the rest of it.
Don't get me started about my VW ID4.
We have some questions in the chat for Paul. I think Paul has answered Gil's question and Aaron's
there was another question: what fraction of customers are microscope cores? I mean, first of all, we're not selling anything. I've never made any money from open scopes or open frame. Other companies are, like Cairn, are selling things, but to my knowledge, there are not many microscopy cores using it. I know that Claire was interested in putting one in her imaging core, but as yet I'm not sure. And I think it's important to understand that we're not trying to compete with the commercial multi-user instruments. And it would be a hard sell. Why would someone want to use our microscope when there's already a, fully engineered user optimized microscope from one of the big vendors? That's not what we're trying to do. If we tried to replicate everything that one of those microscopes did, we'd cost the same, basically. But it's more that with an open frame, you can basically build the thing you need and pay for the functionality you need, and then it can be much cheaper. And if you want it to change, then you can upgrade it, and so on. But what we're we're the open frame, I would say, at least in in relatively affluent countries, isn't an alternative to the existing commercial instruments, because it does something different. However, if you want an instrument that you can rapidly test new microscopy modules on, or scanners, or you want to rapidly implement, then I think it has its place.
Right. With that, we're a minute behind schedule. I again want to thank all three of our speakers, Paul, Nico, and Bryan, as well as everyone in the audience. And have a great rest of everyone's day.
Thank you very much. Cheers.
Thank you.
That was
Bye.
great.
Great talks, everybody. It was really interesting.